know the circuit diagram of bridge. So for the there are the four semiconductor devices are connected in a bridge. Okay, and input is DC supply, so you will get the output. That is the output is the AC. Okay, see here I will show you the circuit diagram. Okay, so this is a DC supply. These are the four switch. These are the IGBTs. Okay, during positive upside during means first period, this SCI, this IGBT and this IGBT will be on. So at that time, current is flowing in this fashion from this to this. Then this and this will be on. Current flows through in a opposite fashion. So means output voltage is both positive and negative. Hello.
हाँ सर, प्रेजेंट के लिखा स्क्रीन.
अरे यार हाँ एक मिनट हाँ. Okay. Are you seeing the screen?
Yes, sir.
So this is a DC. These are the IGBTs. During one means this IGBT and this IGBT will be on. At that time, current is flowing from this side, and then this IGBT and this IGBT will be on. Current is flowing from this side. Means both the side is flowing. So one voltage is a positive voltage, other voltage is the negative voltage. So at the output, you are getting the both the cycle, positive cycle and the negative cycle. Okay. So first we'll see the theory of the PWM inverter. For this, I will run one video on PWM inverter, and after that we'll see how to perform the practical of the PWM inverter by using the multi-sim. So first, it is important. First, you have to understand the working of the circuit. Okay, how the width of pulses will be varied. Then, how you control the fundamental voltage as well as the RMS voltage. So it is very important thing. So first, I am going to run the video.
Problem in the coming lecture. So what I can say, just have a faith on me and start watching this lecture from start to end. And at
Is it audible?
Yes, sir.
Okay.
the end, you will be amazed to see the detailed concept of pulse width modulation. No one has given you in coaching or in book this much amount of concept that I'm going to deliver in the coming
Any doubt?
हाँ सर, फुल स्क्रीन कर सकते हैं? फुल स्क्रीन.
हाँ हाँ ठीक है ठीक.
4 lecture. Got it? So without wasting time, let us start introduction to PWM. So up till now, what we saw in single phase inverter, we saw that the output voltage I am getting in half bridge or full bridge, the waveform, something like this. From 0 to pi, it is VDC for full bridge, and from pi to 2 pi, it is minus VDC for full bridge. Okay. If you consider this half bridge, then it will be plus minus VDC by 2. Got it? This is my output voltage I was getting in single phase inverter that we saw in the previous 4 to 5 lecture, right? And according to this, the Fourier series expression I was getting, that is equal to summation of n is equal to 135.
See here, this upper part. When switch S1 and S2 will be on, at that time you are getting a positive VDC. That is a output voltage is equal to the supply voltage. Means we are making on S1 and S2, and then S3 and S4 will be on. Then current flowing in opposite direction, so that is voltage is negative. So at that time you are getting this part.
Up to infinite 4 VDC upon n pi into sine n omega naught t. This is my Fourier series, right? And total RMS output voltage I was getting for full bridge inverter, that is equal to VDC only. So by using this concept, we can control the switching frequency, no problem. We can turn on and turn off at different switching frequency to get the output voltage at different switching frequency. So we can control the frequency by using this technique. But tell me, can I control the RMS output voltage, or can I control the fundamental component of RMS output voltage, or can I control the fundamental component of peak value of output voltage? Can I control that? No, we cannot control the fundamental output voltage. As we know, V01 is equal to 4 VDC upon pi. Okay, here supply voltage is fixed, means output voltage, fundamental output voltage is fixed. We cannot vary the fundamental output voltage. And because of this nature, I was getting the THD, that is equal to 48.43%. These all concept we saw in the previous 4 lecture, right? So by using this technique, what the problem is? The problem is that we cannot control the fundamental output voltage or RMS output voltage. See, here RMS output voltage is also fixed. So we cannot control the fundamental RMS output voltage or fundamental peak voltage or total RMS voltage. By using this method, we cannot control. Why? Because from 0 to pi, the width of the pulse is fixed. Here, from 0 to pi, it is conducting till 180 degree, and output is I am getting, that is plus VDC. And from pi to 2 pi, it is minus VDC. We cannot control the pulse width of this output voltage, right? That is the reason the fundamental output voltage is fixed, RMS output voltage is fixed. Although we can control the frequency by varying the switching frequency, but we can't control the peak value of output voltage. So this is the disadvantage of using 180 degree conduction mode in single phase inverter. So in order to overcome this disadvantage, what we do, we study the concept of PWM inverter. Don't worry and don't have a fear of this PWM inverter. At the end, you will be amazed to see the concept that I am going to deliver you. Don't worry. Okay. So in order to overcome this disadvantage, we study PWM inverter. That means in PWM inverter, we can control the fundamental output voltage, or we can control the total RMS output voltage. That is for sure. So let us understand which kind of PWM technique we generally do in order to control the fundamental output voltage. See, I am drawing one waveform. This is V naught of t, and it is having a symmetrical waveform in half cycle. One pulse per half cycle. See, per half cycle means from 0 to pi it is giving one pulse, and from pi to 2 pi it is giving one pulse, and it is symmetrical. Symmetrical means it is at 90 degree. 90 degree will be in between this pulse. Okay. So here we define the pulse width. Pulse width is defined as the width of pulse per half cycle. Understand this. Per half cycle means from 0 to pi, how much the width of pulse will be, that is equal to pulse width, right? So see here, from 0 to pi, it is having a pulse width of 2d. So I can write pulse width is equal to 2d. Now what is happening, just understand the concept. If you will find the RMS output voltage of this, then square this waveform, take the average, take the under root, then you will get total RMS output voltage, that is equal to VDC. Let us say this is fluctuating in between plus minus VDC. Okay, so VDC under root of, for how many duration it is conducting, 2d upon pi. Now see, RMS output voltage of this type of waveform depending upon this pulse width. Is it fine? In the earlier case, the pulse width was constant. See, here the pulse width was constant and it is equal to 180 degree. But now in this case, we can vary the pulse width by turning on and turning off the different switch of single phase inverter. Okay, so if I will turn on the S1 and S2 for this duration, then it will give me the output voltage in positive half cycle like this. And if I will turn on the S3 and S4 during negative half cycle, then output voltage I will get that is equal to minus VDC. In earlier case, what I was doing from 0 to pi, I was turning on S1 and S2. That's why I am getting V0 is equal to VDC from 0 to pi. But now in this case, what I will do, I will turn on the S1 and S2 only for fixed duration, and that is symmetrical in nature and having a pulse width of 2D. So because of this, we can vary this pulse width. We can turn on and turn off the switch at 4 different angle in order to get the RMS output voltage different. So we can control the overall RMS output voltage, right? So this disadvantage is being overcome in PWM inverter. We can control the RMS output voltage. So we will see in detail about these all things. This kind of pulse width generally we got in single width modulation. Okay, so this is known as, this is the output voltage waveform of single PWM because it is giving one pulse per half cycle, right? Now see the second part. Second part is that instead of taking one pulse per half cycle, we can increase the number of pulse per half cycle. Okay, and this number of pulse is symmetrical about y-axis. Got it? That means from 0 to pi, I am turning on S1 and S2 for this duration. Then again I am turning on S1 and S2 for this duration. Again I am turning on S1 and S2 for this duration. Means per half cycle, we are turning on and turning off the switch S1 and S2 3 times in order to get the 3 pulse. Are you getting this? In the same way, I am turning on S3 and S4 to get minus VDC. Again, I am turning on S3 and S4 for some duration. Again, I am turning on S3 and S4 for some duration. So this kind of waveform we get generally in multiple PWM. This is known as multiple PWM technique, or you can say multiple pulse width modulation. See here, we are getting multiple pulse per half cycle. In the first case, we are getting single pulse per half cycle. That's why it is single pulse PWM. In the second case, we are getting multiple pulse per half cycle. Then here, what will be the pulse width? See, 2D upon n will give me the width of each pulse, where n is the number of pulse generated per half cycle. Why I am doing like this? Just understand. See, pulse width I defined that width of pulse per half cycle, that is equal to 2D. So see here, in half cycle we are getting 3 pulse. Okay, so each pulse will have pulse width that is equal to 2D by 3, right? In the same way, this pulse will also have 2D by 3 and this pulse will also have 2D by 3. So total pulse width in per half cycle will be equal to 2D. Okay, so I can say if n number of pulse generated in per half cycle, then each pulse width will be equal to 2D upon n. Please keep in mind. Okay, now see the third case. This is also important. Why we are doing these all things? We are doing in order to control the fundamental peak value of output voltage or total RMS output voltage. That is the reason we are doing like this. We are turning on and turning off, or we are doing PWM technique, because here we cannot control the fundamental output voltage just by switching, right? So what we do, we apply the PWM technique in order to get the different pulse per half cycle. So first and second you understood. Now see the third case. Third case is I am turning on S1 and S2 for alpha angle, and I am turning off this. After that I am turning on S3 and S4 from alpha to pi by 2 plus alpha. Again I am turning on S1 and S2, and I am turning off S1 and S2 at pi. Again I am turning off S3 and S4, then again S1 and S2. We know when S1 and S2 will conduct, then output voltage will be plus VDC, and when S3 and S4 will conduct, then output voltage will be minus the VDC. So depending upon this switching cycle, we can turn on and turn off this waveform, right? So this is nothing but PWM technique only, but this is having unequal widths. See here, fixed pulse width is there. Okay, each pulse width are same, but here see the pulse width of this positive cycle is more, pulse width of negative cycle is less. Here pulse width of positive cycle is more. So overall positive area I am getting from 0 to pi greater than the negative area. Now see from the pi to 2 pi, negative area is greater than the positive area. So overall the waveform will be in a downward. So from 0 to pi, overall average output voltage you will get positive, and from pi to 2 pi average output voltage you will get negative. So this kind of waveform generated, that is also known as pulse width modulation, but this pulse width is unequal. Okay, here pulse width is not fixed, this is unequal, and this depends upon the switching. At what point we are turning on S1 and S2, and at what point we are turning off S1 and S2, it depends on this. In the first and second case, the widths of each pulse are same, but in case 3 you can see the width of each pulse are different, right? In the positive half cycle, the overall positive area will be greater. In the negative half cycle, overall negative area will be greater. And this is really important, guys. I can assure you that in any coaching material you want to get this concept, and I will let you know by application of Fourier series. Don't worry. Okay, I will apply the Fourier series, and most of the guys are having fear of Fourier series. So don't worry, I will discuss each and every point. Okay. Fourth point is nothing but sinusoidal PWM modulation. Okay. From here, fourth and fifth point is sinusoidal PWM modulation. That means here reference we take sine wave, and carrier wave we can take triangular or any other. Okay. And we compare those two waves in order to get the output voltage. See, this output voltage is following the sine wave only. If you will find the average output voltage, this is my VDC for T on time, and this is for T of time. So overall output voltage, average output voltage will be somehow something like this. Now see, the pulse width increases. So if the width of the pulse will increase, then overall average output voltage will increase. So average output voltage will increase. Now see here, width of pulse will also it is increases more. Okay. So overall the average output voltage will increase more. In this way, if you will find the average output voltage of this, then it will follow sinusoidal behavior. Okay. So in sinusoidal PWM technique, the width of each pulse is not same. It is different, and the switching frequency is very high. Okay. In per half cycle, you will get, I think, more than hundreds of pulse. So because of that, if you find the average output voltage of each pulse, then you will get the sinusoidal behavior of this. Okay. So this kind of technique is known as unipolar PWM, and this comes under the sinusoidal PWM technique. Sinusoidal PWM technique is divided into two parts, unipolar and bipolar. In the same way, I can vary the pulse width like from plus VDC to minus VDC also. This depends upon the switching of S1, S2, S3, S4. Okay. So when S1, S2 turn on, then positive output voltage will be plus VDC, and when S3, S4 will turn on, then output voltage will be minus VDC. In this way, we can vary the width of each pulse in order to get the sinusoidal behavior, and these two waveform I can easily get by comparing the sine wave with the triangular wave. Okay, see here from 0 to pi, overall the pulse width is more at 90 degree. Okay, this is my pi, let us consider this is my pi. So from 0 to pi, overall output voltage, you can see the pulse width is more at 90 degree, and pulse width is less at 0 degree. So overall it will give you the sinusoidal behavior. I will let you know, I will explain each and every part. I can assure you inverter is the easiest part in power electronics. Just be with me, and in the coming 4 to 5 lectures you will understand each and every point what I am doing. Okay, so this type of technique is known as bipolar PWM technique. Why it is known as bipolar? Because the output voltage I am getting plus VDC as well as minus VDC in per half cycle. But see here in unipolar, the output voltage in half cycle is positive and the next half cycle is negative. That's why it is known as unipolar. So don't worry about these all things. This is the introduction of PWM. I just introduced that in what kind of PWM technique is done. There are different way of doing the PWM, pulse width modulation, in order to get the output voltage controllable. We can control the output voltage, and these all cases we will see in the coming 5 lectures. You don't need to worry about. Got it? So I divided the PWM inverter like this. First, I will talk about the single PWM, then multiple PWM, then we will see the Fourier series, and this is really important. If anyone is having a fear of Fourier series, just watch this lecture. This will be my, I think, the coming lecture. That is the application of Fourier series of unequal PWM. I will give you one short trick. I will explain each and everything of Fourier series that will help you in understanding the analysis of Fourier series, how to find the Fourier series expression of any kind of function. Okay, so don't worry, just be with me. Next is the sinusoidal PWM, in which we will study bipolar and unipolar. Okay, so in the coming lecture we will see the multiple PWM first, and now the student will say that, sir, before starting multiple PWM, please teach a single PWM. If we will not understand single PWM, how can we can understand the multiple PWM? So don't worry about those things. I will start the multiple PWM in the next lecture, and based on that I will derive the Fourier series expression of single PWM, and I am sure you will not get these concepts in any book. I can guarantee you. Okay, in book, if you will see in Vimra, then they have explained the multiple PWM by taking 2 pulse. But if in the GATE exam, if they will give you the 3 pulse, then what will you do, right? So this is the disadvantage for the student if they will go and study with the book. Okay, so I will explain you each and everything, don't worry. But before that, as I explain you that I am getting these kind of pulse. Okay, so there is some method to generate this kind of pulse, right? So that we are going to see how to generate this symmetrical pulse, means point number 1 and point number 2. So see here, I am taking the 2 waveform. One is the square waveform. This is known as the reference waveform. Okay. Second one I am taking, that is the triangular waveform known as carrier waveform. Okay. So what I do, just understand the concept. I take one square waveform and I take one carrier waveform that is triangular in nature, like this, and I pass these two with comparator. Okay, what is comparator? You have studied in analog electronics. What is comparator? Comparator just compare the value of these two waveforms, and after passing these two waveforms from the comparator, and this comparator is something like this. If the carrier wave, means if VC will be greater than the reference wave, that is the square wave. This square wave is the VR, and this carrier wave having instantaneous value VC. Okay, so if VC is greater than VR, then at that time trigger the S1 and S2 for positive half cycle, and for negative half cycle also I can take like this. If minus VC is greater than minus VR, then trigger S3 and S4. Are you getting this? So if VC will be greater than VR, then S1 and S2 will trigger, and the moment when S1 S2 will be triggered, then output voltage I will get, that is equal to VDC. That we have seen in the previous 4 to 5 lecture. In the same way, if minus VC is greater than minus VR, then S3 S4 will turn on, and in this case output voltage will be equal to minus VDC. Okay, so I pass these two waveform with comparator, and I do the coding like this. Okay, in order to trigger the 4 switch of single phase full bridge inverter. So see here, after this point and after before this point, the carrier voltage is greater than the reference voltage. So when carrier voltage is greater than the reference voltage, then output voltage I will get, that is equal to VDC. This is my VDC. In the same way, this is the carrier voltage is greater than the reference voltage from this range. So output voltage I am getting something like this. In the same way, output voltage I am getting something like this. So this is the output voltage of multiple PWM technique. Okay. In the same way, from pi to 2 pi, I did the coding like if minus VC is greater than minus VR, then S3 S4 will be on, and when this S3 S4 will be on, then V0 will be minus VDC. So see here, V0 will be minus VDC when minus VC is greater than minus VR. So this is my minus VDC, this is my minus VDC, this is my minus VDC. In this way, we can generate the pulse. Now here question arises, how to find the number of pulse? So I denote the number of pulse, that is equal to n. Okay, we are getting 3 pulse, that means here 3 cycle of carrier wave I am getting, right? So let us understand total pulse width in half cycle. I already explained you, that is equal to 2D, right? So each pulse width is having, that is equal to 2D upon n, where n is the number of pulse. Means the width of each pulse will be equal to 2D upon n. Okay. Now I need to find the number of pulse in. How we can find the number of pulse in? So what I will do, just see from 0 to pi. From 0 to pi, let us say the time period of this reference wave is TR and time period of this carrier wave is TC. Okay. So 3 times of time period of carrier wave is equal to TR by 2. You can see that this is my TR by 2. Reference wave having time period from here to here. एक बुल को ऊपर एसिड फेंक दिया, एसिड पूरा शरीर में जल चुका, तो उसको हमने ट्रीटमेंट करके सक्सेसफुली वो अभी बुल इज डूइंग वेल, वी आर टेकिंग केयर. Okay, this is my TR, and from 0 to pi it will be TR by 2, and in between TR by 2 from 0 to pi you can see 3 TC is there. This is the time period of carrier frequency. So I can write 3 TC is equal to TR by 2. That 3 is equal to TR can be replaced by, that is equal to 1 upon FR, and TC can be replaced by 1 upon FC. So it will be equal to FC upon 2 FR, and this 3 is nothing but number of pulse in half cycle, that is equal to N. So in order to get the number of pulse per half cycle, N will be equal to carrier frequency upon 2 times of reference frequency. Here reference wave is a square wave and carrier wave is the triangular wave. Got it? So in this way we can find the number of pulse. So this is really important. Take it in your notes. Now the second question is how to find the each pulse width. I told you that each pulse width is having 2D by N. Okay. So I am going to find the width of each pulse. So let us understand this. This is really important. See, this width I need to find, means I need to find this point. So take this reference wave and take this carrier wave. One carrier wave, you can take it like this. This is my carrier wave, and let us say this is my reference wave having value VR, and this is my width of each pulse. Now understand how to find the pulse width of each pulse. Okay. So let us take this value. What is the value of this? See, we are getting the triangular wave, 3 triangular wave. So each triangular wave will be equal to pi by n duration. This will be my pi by n. Now see the magnitude this. This is my Vc, and this is my magnitude Vc minus Vr. Right? Now apply the similar triangle concept. This is, let us take ABC, and this D, and this is E point. So ADE is similar to triangle ABC, right? So I can write, let us consider this is my altitude, okay, or you can say this is my height of triangle ADE, and this is my height of triangle ABC. So apply similar triangle concept. Let us say this is my point O. So I can write OA upon AM is equal to.
Hello, welcome to the postgraduate program in Artificial Intelligence and Machine Learning offered by the University of Texas at Austin in collaboration with Great Learning.
DE upon VC, I can write according to similarity, right? So OA is nothing but VC minus VR. So this is written as VC minus VR upon total is VC is equal to DE is the width of each pulse. So let us denote that as W, width of each pulse, upon BC I can write that is equal to pi by n. So from here you can easily get width of each pulse, that is equal to W, that is equal to pi by n, 1 minus VR upon VC. Now this VR upon VC is nothing but modulation index. So pi by n into minus m, and you can see this is under modulation because here VR is less than VC, so m will be less than 1. So width of each pulse will be equal to pi by n into 1 minus m, where n is the number of pulse, and number of pulse we can find by comparing the frequency of carrier and reference, that is equal to FC upon 2FR. So these two formula you need to keep in mind. The question may be framed from these two formula. Got it? So based on the concept which we have studied today, let us take this homework, and you have to solve this homework, and you have to write the answer of this homework in YouTube comment. So that's all about this lecture. In the next lecture, we will start the multiple PWM technique. Before starting single PWM, I will derive the expression of multiple PWM. Then we will move to the single PWM. Got it? So if you guys understood the concept, then please like this video and share this all video with your juniors and friends. For doubt solving, you can join our Facebook group.
Okay, are you understand the concept of the pulse width modulation?
Yes, sir.
Okay. Now we'll see the next video that is about the PWM.
The first day of classes filled with possibilities as well as unknown. That's why Check Study Pack empowers you with comprehensive study solutions and expert Q&A, so you know you've got this from the very start. Crushing it.
Hi guys, welcome to Getmatic. In the previous lecture, we saw the introduction of PWM and what kind of PWM technique is done, why PWM technique is applied. These all things, that is the basic of PWM we saw in the previous lecture. Now in this lecture, we will start a multiple PWM technique. So let's get started. So this is my output voltage.
Are you seeing the screen? Anybody?
Yes, sir.
Okay.
Got in multiple PWM technique and how we can generate this output voltage, that I have already explained you in the previous lecture, that is the lecture number 40. From 0 to pi, you can pulse width is 2D. I already defined that the 2D is equal to the pulse width per half cycle. So each pulse width is having 2D upon n. This is all concept I explained you in the previous lecture. This is my 2D upon n, where n is equal to 3 by taking this waveform. Okay. So this is my example of multiple PWM. So in multiple PWM technique, you can see here each pulse width is same. The space width are also equal. This is my space width. This is my space width. This is my space width and this is my space width. So per half cycle we are getting 4 space width for n is equal to 3. Are you getting this? And gamma, let us denote this parameter. This is my gamma. Gamma is the angle from 0 to half of pulse width. Okay, this is my gamma. Are you getting this? So these all things you should know, because in order to derive the Fourier series expression, you need to know these things. So each pulse width is equal to 2D upon n. I know this. In the same way, I can say each space width. Space width is equal to this much, this much, this much, and this much, and these are equal. So space width I can write, see here, this is my gamma, right? And half of the pulse width I can easily say d by n is the half of pulse width. So I can say gamma minus d by n will give me the each space width. So I can write gamma minus d by n. Now my aim is to find the value of this gamma. Okay. So how will I find? Let us understand. Here for 3 pulse widths we are getting 4 space width. So I can say total space width will be equal to 4, and this 4 will be equal to n plus 1. See here, for 3 pulse width we are getting 4 space width. That means I can write like n plus 1. Okay. Now what you can write till pi, see 4 multiplied by gamma minus d by n. This is my total space width. plus total pulse width. Total pulse width will be 2d. 2d by n plus 2d by n plus 2bd by n, that is equal to 6d by n. Put the value of n is equal to 3. You will get pulse width that is equal to 2d only. Okay, that is equal to pi. I can write like this. Now I can replace this 4 with n plus 1. I can replace like this, n plus 1 into gamma minus d by n plus per half cycle. I know the pulse width is 2d equal to pi. So from here I can easily get gamma that is equal to pi minus 2d upon n plus 1 plus d by n. This is really important. If you see the PS Mimra, you will not able to understand because they derive the expression for pi considering 2 pulse. Okay, and they give the general formula of gamma that is equal to this much. So you have to mug up. I have solved the problem of yours. What you can do? You can proceed like this in order to find the gamma that is equal to pi minus 2d by n plus 1 plus d by n, where n is the number of pulse. In this way, we can find the value of gamma. Now the question arises that why we are finding the gamma? What is the benefit of finding the gamma, right? So let us understand that I need to find the Fourier series expression of this multiple pulse width modulation. So how will I find that? We are going to see. So first see, this function is half wave symmetry or not. Of course this function is half wave symmetry. This is the mathematical part of Fourier series, and I will explain this in lecture number 42. Don't worry. Okay. Till now, just understand that half wave symmetry, the condition of half wave symmetry is f of theta is equal to minus of f of pi plus theta. Means if I will find the value at angle this theta, let us consider this is my angle theta. Okay, then pi plus theta will be somehow here. Okay, so minus of f of pi plus theta, then it is satisfying. So this is my half wave symmetry, that is denoted as HWS. I will explain each and everything of Fourier series in lecture number 42. Don't worry, till now you should know that this is half wave symmetry. Okay. Also this is odd function. So odd function plus half wave symmetry means this will give only Bn in Fourier series, and A0 and An will be equal to 0. So what is the value of Bn that we are going to find? So Bn will be equal to 2 upon 2 pi. It is having some limit. I don't want to explain now. And this is having peak voltage that is equal to, let us say, VDC, and this is minus VDC. So this is equal to VDC into sine n omega t into d omega t, right? Now how to take the limit? See, I am taking one cycle only. Okay, so if I will take one cycle, then this cycle is at from gamma minus d by n to gamma plus d by n. If I will consider this cycles, then the limit will be gamma minus d by n to gamma plus d by n. I can write like this, and this is the Bn of this pulse width, right? So if I need to find the Bn of total pulse width per half cycle, then what I need to do? I need to multiply by n. So this is the generalized expression of Bn. Are you getting this? Please understand each and every point so that you will not have any problem later on. Okay. So this is the Bn of each pulse width, and if I will multiply this with n, then I will get the Bn of total pulse width. Now, according to half wave symmetry, I know I need to multiply this by 2 also. If you are having any doubt in writing these things, then just wait for the next lecture, that is the lecture number 42. I will explain each and every concept. Up till now, you should note down how this is coming. Okay. Why I am multiplying this by 2? See, I am finding the Bn up to pi only. From pi to 2 pi, I am not finding. So from pi to 2 pi also, the Bn will remain same that we are getting from 0 to pi. That's why I am multiplying this by 2. Got it? This all concept I will explain you in application of Fourier series, that is the next lecture. Up till now, just understand how to find the value of Bn in Fourier series expression. So if I will find the value of Bn, then I can easily write V0 of t is equal to summation of n is equal to 135 up to infinite Bn sin n omega naught t. This is my total Fourier series expression. As we know that a naught and an will be equal to 0 for half wave symmetry. Also, for half wave symmetry, there is the one features of half wave symmetry that there will be no any even harmonics. Okay, so mug up these things. I will explain you in lecture number 42 that there will be no any even harmonics present in half wave symmetry. So this is my Fourier expression of Bn. Now solve this expression. It will be equal to cos n gamma minus d by n minus cos n gamma plus d by n. Now do mathematics. It will be equal to 2n VDC upon n pi. Now you can manipulate this cos a minus b. So it will be cos a cos b plus sin a sin b, and cos a plus b. It is cos a cos b minus sin a sin b. So if you will do this, then cos n gamma and cos n d by n will get cancelled out. Overall, you will get 2 sin n gamma into sin n d by n. 2 will come out outside. It will be equal to n multiplied by 4 VDC upon n pi sin n gamma into sin n d by n. This is my peak value of fundamental output voltage, that is also denoted as V01 of A. Okay, so Bn is nothing but V01 of A. Here capital N is the number of pulses per half cycle and small n is the harmonic number. Okay, so what is the final Fourier series expression of this kind of waveform? Kind of waveform is having final Fourier series expression. This is my generalized expression. For any value of n, you can apply this Fourier series, that is equal to n multiplied by summation of n is equal to 135 up to infinite 4 VDC upon n pi sin n gamma sin n d by n. So this is the generalized expression of multiple PWM technique. This is my analysis, and I derived this just by generalizing each and every term in order to get the Fourier series expression of multiple PWM. Now, if you want to take 2 pulses, no problem, take n is equal to 2, write down the Fourier series expression. If you want to take 1 pulse, no problem, take n is equal to 1 and write down the Fourier series expression. So is it necessary that I need to explain the single PWM technique? What is single PWM technique? That I already explained you in the previous lecture. That is the point number 1. This is my single PWM technique. Here 1 pulse width per half cycle. Okay, so what is the value of n? The value of n will be equal to 1. So for single PWM technique, I am omitting this. For single PWM technique, the value of n will be equal to 1. Now tell me what is the value of gamma. Gamma will be equal to pi minus 2d upon n plus 1 plus d by n. Right? Put n is equal to 1, it will be equal to pi by 2 minus d plus d. So gamma will come out to be pi by 2. So what is the Fourier series expression? Part of t will be equal to, put capital N is equal to 1 in this expression. It will be equal to summation of n is equal to 135 up to infinite 4 VDC upon n pi sin n gamma. Here gamma is pi by 2. That means sin n pi by 2 we know that is equal to 1 and sin n d. So this will be equal to sin n d. That's all. So in each and every book you will see they have derived the Fourier series expression of single PWM, but they haven't derived the Fourier series expression of multiple PWM. If you know the Fourier series expression of multiple PWM, then do you need to mug up the Fourier series expression of single PWM? No, I don't think so. Just you need to put the value of n, and based on that you can find each and every parameter. Got it? So you need to understand this, how this is coming. I already explained you in this lecture how this is coming, and you need to understand why we are finding the gamma. Got it? That is the reason I explained the concept of multi PWM first, and then I told you that in single PWM only you need to put the value of n is equal to 1 to get the Fourier series expression of single PWM. And this is really important from gate point of view. This is not important. For multiple PWM technique is not important from gate point of view. But still, I don't want to left any topic from inverter, because I already told you that in gate 2018 they have not asked the questions from inverter. So definitely they are going to ask the questions from inverter in gate 2019. That's why I'm not skipping any point. Got it? Now you need to find the Fourier series expression of this. Let us consider the 2 pulse, and this is the equal width pulse. Okay, separated by equal distance. This is my 2 pulse, means here n is equal to 2. So you can write the Fourier series expression for 2 pulse PWM also, that is equal to. So this is the Fourier series expression for 2 pulse PWM, right? In each half cycle, we are getting 2 pulse. So this is my n is equal to 2, and this is my n is equal to 1. So in PS Vimra, or if you will see any book, then you will get the Fourier series expression of this 2 pulse converter like this, and they have explained by taking multiple PWM. So if any guy will go through the book and they will see the Fourier series expression of multiple PWM that is equal to this much, then they will apply this formula directly in multiple PWM. But this will be wrong. Why? Because this is only for 2 pulse per half cycle. If I will give you the questions for 3 pulse, then this formula is not valid. Are you getting this? So do not mug up these things, guys. I am again telling you, just see the generalized expression and see this expression. If you know this expression, then you can find the Fourier series expression of any kind of multiple PWM. Got it? Now,
Okay, are you understand the concept of the pulse width modulation? That is single pulse, multi-pulse. Okay, so next time we'll see how it perform by using the multi-sim software. So now you have to give your attendance, means you have to write down your roll numbers in the chat box. If you have any doubt, you can ask me. Write down the roll numbers in chat box. If you don't have any doubt, you can leave the meeting. If you have any doubt, you can ask me.